So let's get started. So like I said, exam 1 is Thursday the 10th. I'll review it real quick. Exam 1 is Thursday the 10th. You'll use Respondus Monitor. We won't be meeting at all on Thursday, September 10th. On Tuesday the 8th, we will only be meeting digitally, and you can submit photos of your work to me for exam 1. You'll see where all of that is in the Canvas modules. Okay, so let me bring up the notes for our course. We're continuing on from where we stopped last class, and last time we were talking about real numbers, the real number system. We looked at a few real number properties, and we said, oh, those are pretty interesting. And so now we're going to continue on with those ideas. So there you go. Okay, so we mentioned a few of the properties of real numbers. We had several sheets of it. The closure property, those weren't super interesting. Commutative property of addition, multiplication, you can flip the order in which you do them and it's the same thing. Those were somewhat interesting, a little bit more. Associative property, the distributive property, now we're starting to cook with oil because that's starting to get interesting to us. Various identity properties, if you add 0 to a number, it doesn't change the number. For multiplication, the identity would be 1. If you multiply a number by 1, it stays the same thing, the exact same thing. And then inverse properties, if you want to add something to a number and get it down to 0, you got to add the opposite sign of it. So the inverse of square root of 3 is the negative square root of 3. The inverse of negative 17 is positive 17. We're going to be invoking that a lot. And then finally, we're going to talk about the inverse property of multiplication. We're going to be using these, especially these here, in order to solve equations. That's going to be our goal. And we will get to that goal at some point. So we can play around with some of these. We can name the properties. If you switch the order of multiplication, so square root of 3 times 7 is equal to 7 times the square root of 3, 7. All you did was change the order of them, so you were dealing with the commutative property of multiplication. You can see there's a couple other things. The distributive property here, we distributed the 2, so it became 2 times 3 plus 2 times the square root of 5. 2 times 3, of course, is 6. 2 times the square root of 5, though, isn't anything slick. It's just 2 square roots of 5. And then finally, if you start with 17 and you add to it its flipped sign number, negative 17, that comes out to 0. You can also realize that that very quickly lends itself to just saying, well, that's just 17 minus 17. That's exactly right. When you add a negative number, you could just call it subtraction if you wanted to. And that's really what we're going to be doing. We're not going to get so cute with all of that. Why do we care about this? How are we going to ever use any of this information? Well, let's say we were solving an equation and we're peering ahead a little bit. We're looking a little bit into the future. Let's say we had a simple enough equation, 3x plus 14 equals 9. 3x plus 14 is equal to 9. Now here's what we'd like to do. When we're solving an equation, we are looking to isolate the variable, if possible. And what we're truly, honestly, at the end of the day doing, we are trying to figure out what is a numerical value that I can plug into the variable all the way back at the original equation, that's going to make that equation a true statement and not a liar. We don't want our equations to be liars. We want them to be truth tellers. So that's exactly what we are looking to do. The way we're going to do that is we're going to use several properties. So we want to isolate the variable. Our variable is clearly x. The way we can do that, Will, you might have seen this before, but what you can see is that we have plus 14 over there. I want to get rid of that. So I'm going to get rid of that. You could say I'm going to add negative 14 to both sides, but don't overthink it. Just say I'm going to subtract 14 from both sides. What that's going to do is, thanks to that inverse property of addition, this part is going to go away. In fact, that's the whole reason I did it, was because that helps me get my x by itself. What's left is 3x on the left. Now we do need to do the 9 minus 14 on the right. I can tell I'm taking a larger number away from a smaller number. So am I going to have a positive or a negative outcome here? Negative, exactly. And now that I know it, then I can secretly do the 14 minus 9. I can kind of flip them on their heads. So I'm going to have 3x equals negative 5. Now, what do you think I need to do next here? We're going to divide it by 3. Exactly. That's actually going to be using the inverse property of multiplication. Look, our x, our variable x, is being multiplied by 3. I want to get rid of that 3 because I want x by itself. The way I'm going to do that, since it's being multiplied by 3, I need to get rid of that 3. I don't subtract it over. Instead, I use the inverse property of multiplication, and I multiply it by its reciprocal. And I have to do it fairly to both sides of the equation. Now, you could just say that's the same as dividing by 3, and I say, I agree. We talked about that last time. Dividing by a number is the same as multiplying by the reciprocal. However you want to call it, whatever you're comfortable with, is totally up to you. So, thanks to the inverse property, those are going to be gone over here. You're just going to have x by itself. On the right-hand side, you could call that negative 5 over 1 times 1/3. And so you just have negative 5/3. And that's going to be your answer here. So that's how we solve equations. You've probably seen something like that before. How do we know that negative 5/3 works? Exactly. Go back all the way to your original equation, which was 3x plus 14 equals 9. Go all the way back. So we started with 3x plus 14 equals 9. Take your proposed solution, what you suspect is the solution, and plug it in for x. And if you produce a true statement out of that, you've got it. So that would become 3 times negative 5/3 plus 14. And we're asking now, does that equal, I'm going to put a nice question mark over it, does that equal 9? Well, we can cross multiply. We can say that 3 is really 3 over 1. These 3's actually cancel according to cross multiplication. You're just left with negative 5 here. You could say it's negative 5 over 1, but it's the same thing as just calling it negative 5. Plus 14, we're asking, is that equal to 9? And yes, it is. On the left-hand side, negative 5 plus 14 is the same as 14 minus 5. Exact same thing, which equals 9. So I'm going to put a big fat check mark and say, yes, 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 we confirmed it. Negative 5 over 3 is indeed a solution to the original equation, 3x plus 14 equals 9. Any questions on that? You can use the text box, or you can ask me here in person. Either way is golden for me. I'll give you about 10 more seconds just to see. Okay, so let's move right along. We've finished what we're going to cover in chapter 5 so far. We've finished it. Now, give me 1 second. Let me check on something technical here. I like keeping my iPad so that I can see what you guys see. I use a separate login, so it doesn't know it's me. I log in, I watch it on my iPad and make sure that it's looking correct. And it just makes our lives a little easier this way. Okay, so moving on, we're now going to look at chapter 6. So let me pull the notes up for that. And it's going to get pretty intense in chapter 6. Just like how camping usually is intense. I guess you can use a cabin, but it's just not as fun that way, right? So, as I buy time with my corny jokes. So, back to it. So we're going to get into some pretty heavy-hitting algebra. We're going to look at algebra. Now, a lot of people ask me, they say, and by a lot of people I mean very few people, but whatever I'm going to say. A lot of people, they say, Josh, what is algebra? That's actually a lot harder to define than you think. A lot of people think that algebra ends with algebra 2 in high school. And that's actually not true. Algebra is actually a really, really, really large, deep field in mathematics that has research being done in it today by super duper smart PhDs and doctors only, math doctorates. So algebra is not quite as simple as we think. What we're going to be studying is kind of the building blocks of algebra. We're going to see how we build it up. But if you want like a major overarching idea of what algebra is, a lot of algebra is concerned with setting up equations that have variables in them and finding ways to solve them. That's a very broad definition. That's not the definition of algebra. But that's kind of what's going on when we do that. So let's look at algebra more specifically. So we've already kind of touched on it a little bit, but ultimately algebra is all about using letters, which we call variables, such as x and y, and they're meant to represent numbers. Variables that are meant to represent numbers. You can use x, you can use y, you can use z. You can use A, B, C, D. You can use any letter you want. You can use Greek letters. Greek letters, you can use pi. Of course, pi is the constant in math that we talked about last time, about 3.14, and then remember, it goes on forever and ever and ever with no repeating pattern, because pi is an irrational number. So you can do that. Other Greek letters you might use, theta. There's all kinds you could use. You can use alpha is popular. But the point is, it's just a letter, it's just a symbol meant to represent a number, but you don't know what the number is, at least at the get-go. That's kind of the point of the variable. And the reason we do that is because there's a lot of situations in mathematics, and really thus as a reflection of real life, there's a lot of situations where you're not going to know the answer to something. The whole point is that you're using some form of reasoning to find the answer. There's interesting examples too. Let me pull one up here for you. Let's say that you have a fence. Let's say you have a rectangular fence. You're making a rectangular fence. A rectangle has a length and a width. So this might be the length, this might be the width over here. Now, you want to get a certain area in there. You want to get a certain area. Let's say you want the inside of your fencing area. Let's say you've got some pigs or something. Let's say you want 108 square feet in there. 108 square feet. And let's also say that you've got 500 feet of fencing available. 500 feet of fencing available. Well, how do you know what you should make the length of the fence, and how do you know what you should make the width of the fence? Well, there's really, you can just guess, but that's not a good method in the long run, especially as these things get nastier and nastier. You can just guess, or you can introduce some variables. You can say, let's call the length X. Let's call the width of the rectangle Y. If I know I have 500 feet of fencing, that's going to be the perimeter of the fence. That's got to be what it is. So there's a couple equations I can set up just from knowing this basic situation. One of them is I know that the length X plus the width, but then because this would also be X, this would also be Y, I got to add all four sides together. I know that that needs to equal what number? 500, exactly. Because 500 is how much fencing I have available, how much physical fence I have in that's going to create the perimeter. What we can see is there's two X's there, there's two Y's there. So I can use what we call combining like terms, and we'll discuss that here in this course. I can use combining of like terms to condense that down to a slightly simpler equation, but it's the same equation in spirit as this one. So here's one equation I can use to model this situation. What's another equation just using the information on the board that I can set up here? Not quite X squared, but you're on the right track. The area of the rectangular prism, of the rectangle rather, has to be 108, right? The area is found by multiplying the length by the width, and you don't need to do it twice or anything. So X times Y is supposed to equal what? 108. And suddenly I've established two equations here. Two different equations here that model this situation perfectly and exactly. How do I actually solve this and figure out what X and Y need to be? Well, that's actually a loaded question. Turns out there's a lot of things you can choose for X, and then Y is forced to be something else that satisfies those two equations. If I said something like the length has to be exactly twice the width for whatever reason, then I can suddenly narrow it down and there's only certain things that X and Y can be. So we're not actually solving anything at this juncture. We're simply looking at it. We're looking at it, seeing what we could model with algebra. So all an algebraic expression is it's a combination of variables, however many you have. In that last example we just looked at, we had X's and we have Y's. It's a combination of variables and numbers using addition, subtraction, multiplication, or division, and you can also use exponents, powers. You can use roots, square roots, whatever kind of roots you like. And then any combination of those things together creates an algebraic expression. So square root of X, and then outside of that, plus 7, this is an expression, absolutely. The number 6 times X, sure, that's an expression. Even something nasty. Even something, let's close that. Even something that's just not super pretty, like I don't know, something nasty like that. How many of you would look at that and say, that's nasty? How many of you would say, that's some nasty nast? I agree, it is nasty, it's not pretty, but it is technically an algebraic expression, because all it does is it involves variables. In this case, it only has one, but heck, we can throw another one in there. How about 3y to the 7th? It involves variables, numbers, combinations of them, adding, subtracting, multiplying, dividing, taking square roots. None in this case, but heck, boom, throw a square root in there, go crazy. Those are algebraic expressions. So it's just an expression. There's a subtle difference between an expression and an equation. If you had an equation, you have to have an equal sign, and then you can put something over there. It could be some other algebraic expression like this. 2x squared plus 7y equals the square root of, y to the 7 minus blah, 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 all that nastiness. Now you're talking about an equation. When you bring an equation into bear, the equation doesn't have to have anything on the other side either. You can just put a 0 over there and it's still an equation. And in fact, that's usually what we want. We want to get everything on one side of the equation and a 0 on the other side, depending on what we're doing. So if you were just looking at an algebraic expression like this thing here, or down here, the x plus 6 by itself, the x squared minus 6 by itself, there's nothing to solve. There's nothing to solve. Now you might plug numbers in for the variables, but it's not like we're solving this. You're only solving it if you're bringing an equation into it, or perhaps an inequality, less than or equal to, something like that. Then maybe you can talk about solving that. But if it's just a singular thing, you're not exactly solving. So don't let that throw you off. Don't let it throw you off. Okay. So order of operations, we kind of talked about order of operations before, we mentioned it. We remember that there was this cute little way to remember PEMDAS. Please excuse my dear Aunt Sally. I put the MD next to each other because we do multiplication and division in the same stage. We just do it from left to right. Same for addition, subtraction. We do it from left to right. You should have seen a good bit of order of operations problems in your homework so far. So now we're going to expand that a little bit and do the PEMDAS. We're going to expand that a little bit and see just how far down the rabbit hole we can go. So for one, we can use function evaluation. So it says evaluate the expression 7 plus 5 times, in parentheses, x minus 4 cubed. We want to evaluate it for x equals 6. What the heck is that talking about? Well, what they're saying is this is the expression here. That's the expression. When it says evaluate, it's saying, hey, whatever you've got for the variable, a 6, all right, pop that 6 right in for the variable. Plug it in, plug it in. How many of you remember that? Anyone maybe remember that as like Glade plugins? That might be from a little bit before your time out there. Of course, I'm actually very old. Did I say the joke last time that I was 18? Did I say that joke? Was that in this class that I said I was 18? Not true. I'm actually 457. I'm 457 years old. You're probably thinking, Josh, you don't look bad. You look about 31, which is my real age. You don't look bad for 457. How do you do it, Josh? And I say, well, it's magic. It's blood magic specifically. It's not very clean. It's not something I want to go into. It's a very dark part of my life. None of that's true. It's not magic. I don't believe in magic. I'm not weird like that. No, I'm not 457 years old. That's okay, so yes, thank you, Xavier. Yes, I did mention last time I was 18. I'm actually 457. Not really, I'm actually 31. Okay, so moving on from that business. So what we're doing is we're plugging a 6 in for the variable. Now, if we had two variables in that expression, they would need to give us direction, hey, plug a 6 in for x and a -3 in for y. They would need to, give you more than just one variable in that case. So the way it works, we're going to follow our proper order of operations. We'll get John Madden here. We're going to plug that 6 in for x here. Boom, and now there's no variable anymore. It's still technically just an expression, but we're evaluating it. So please excuse my dear Aunt Sally, P for parentheses, we do what's in parentheses first. We do the 6 minus 4 first, and we get 2. So it simplifies down to this form. We've taken care of everything in parentheses. There's still a parentheses on the map, on the board, that 2, but there's no actual operation going on inside the parentheses, so we're done with the P stage. Next up, we got to do 2 cubed. I don't do the 7 plus 5 first. I don't do 5 times that business first. I do the 2 cubed first. And you'll recall from exponents, 2 cubed means multiply 2 to itself 3 total times. 2 times 2 is 4, times 2 again is 8. So that's where they're getting this 8 here. So we've taken care of parentheses, we've taken care of exponents. Now again, you don't just do the 7 plus 5 yet because of order of operations. Our next order is to do multiplication or division. So I need to do the 5 times 8 first and get 40. Finally, I do 7 plus 40. That I can do at the very end, and I get 47. So if there's a problem that says evaluate 7 plus 5 times x minus 4 cubed for x equals 6, this is how you'd follow it. You end up with 47. And that's about as much interesting things I can say about that. Any questions on that so far? This all tracking pretty well, pretty straightforward. Good. Hopefully, ideally, a lot of what we're covering so far is a little bit of review, maybe review that we're taking an extra step or two on and seeing it go a little farther. But ultimately, this is just review, hopefully. If it's new to you, that's totally fine. That's what we're here for in this class, is to teach you some new math. When we get to the 1332 portion of the course, we're definitely going to be talking about more advanced stuff. We're going to be talking about financial equations and things like that, things of that nature. And they most likely will be things you have not seen before. So, as I mentioned before, as I promised before, an equation is simply two mathematical expressions with an equal sign somewhere in between them, an equal sign separating them. You see the word equation, it looks like it's almost spelling the word equal in there, and that's exactly what's happening. So again, if you don't have an equal sign, if you don't have what is called an inequality that we'll talk about eventually, you don't have anything special going on. You just have an expression, and it's just like, okay, that's cool, you have an expression, thank you. It's not until you bring equations into it that things might start getting a little bit interesting. So a formula is simply an equation that that expresses a relationship between variables. So it's almost not worth defining what a formula is. But mathematical modeling is super interesting. When we talked about that fence example earlier, we modeled a real world situation. We said, hey, look, we got this much fencing. We need to enclose this much area, because that's how much area our goats need, something like that. How can we do it? What are the ways we can do it? Mathematical process modeling is just the process of finding formulas, finding equations or inequalities, whatever it is, to describe real world things, real world. So it's not cool. There's no math models like they walk down a runway or anything like that. That's not how it works exactly. Instead, it's really just that. Pretty straightforward. So we look at this and, oh my goodness, all of a sudden we're bringing in a nasty equation into that. That's okay, let's take it slowly. The bar graph shows the estimated number of calories per day needed to maintain proper energy levels, whatever you want to call it, for various gender and age groups for an active lifestyle. So, some of you people know, as all of you probably know, calories are the energy units of our food, basically. That's how we measure them. The more food you eat, theoretically, the more your body can turn that into energy. And if you're staying active and you're, I don't know, bicycling, I used to go to the gym before a pandemic hit, and that was great. I loved going to the gym. It was a lot of fun. Now I'm a hypochondriac. I'm afraid to go anywhere near the gym, but man, I really miss the gym. It was a lot of fun. I would just go in. I would just get on the elliptical. I'm already forgetting the gym terms. Get on the elliptical for 30 minutes. I'd watch something on Hulu or, just play around with it. I'd do some weights. It was a lot of fun and I miss it. But I do remember when I was going to the gym 4 times a week and I was being religious about it, man, I ate a lot of food. I ate tons of food. Unfortunately, it was mostly Taco Bell. It was almost all Taco Bell. So I was going out and working out, but I wasn't maybe eating the proper diet. Anywho, so the more active you are, the more calories you need. So we can look at this bar graph. And for people in the age range of 4 to 8, they need both boys and girls need about 1,500 calories per day. In the 19 to 30 range, which I can no longer claim membership in, women need about 2,100 calories a day. If they're at a moderate level of activity, men need about 2,700 calories. And that's unfair because I have friends who they'll use MyFitnessPal and they're dieting and stuff. And I have female friends and then they'll go, why do you get to eat almost twice as many calories as me? And it's like, well, I don't know. Because that's just unfair, isn't it? It sucks. Nobody's having fun on a diet, I can promise you that. So ultimately, this is a nice little bar graph. We can read off of it, but we actually have an equation. We have an equation that can actually model this for us. So it describes the number of calories needed per day by women in a certain age group with moderately active lifestyles. So if you are in group 4 here, if you are in group 4 in the 19 to 30 range and you are a woman, you would use this equation to describe roughly how many calories you need. So you could say W equals negative 66 times, you're in the group 4. So it would look like that. Let's see if I can't move this. So it's a little easier to see. Maybe that's a little bit better. Plus 526 times 4 plus 1,030. Now this is one where the numbers might just be begging for a calculator. You don't exactly have a calculator that you're allowed to use for this portion of the course, certainly not on exams. So it's begging for a calculator, but we can't quite use one. But if we were to do the numbers, I guess I'll do them real quick. I'll use my calculator. Okay, let's go into the side mode. 1056. Give me 1 second. Then, if you're in group 4 and a woman, you can have about 2078 calories per day. That's about right for you. So this one just rounded up on the chart to 2,100. But what we did, all we had here was a mathematical model at the end of the day. X, the independent variable, is whichever group number you're in, group 1, group 2, group 3, group 4. And you'd plug it in and you could tell you it would spit out W, the number of calories a woman in that age group can generally have and be fine in terms of having an active lifestyle. So kind of interesting. As we said, oh, look, they did it over here. Cool. You're in group 4, so you plug a 4 in for X. That's what it did down here. Figure it out, simplify it. You get 2,078 and call it a day. So mathematical models are very valuable. It's really kind of the whole point of math. The whole point of math, well, there's 2 possibilities. Either A, Math is designed to frustrate you and anger you and cause you a lot of agitation. How many of you think that's what math is for? Pretend like pretend like the answer is no to that question. Say, no, Josh, no, none of us believe that. Ha ha. No, I understand. Yes, math can be a little bit frustrating. I think a lot of that stems. Look, I'm going to say this and take it with a grain of salt. I don't think math is super difficult at the end of the day. Of course, I've studied it, right? So yeah, oh, this guy's going to come in and he studied math his whole life. He's going to tell us that math is easy. No, I'm not quite saying that. I'm saying you need a ground up approach. You need a building blocks approach to math. And I think a lot of the times we don't get that. And so that does cause a lot of agitation and stress. So some of the vocabulary that we'll be throwing around here. Let's see what we've got. A term is just a separate part of an algebraic expression separated by addition or subtraction. So 7x, that means 7 times x. That means 7 multiplied to x. But since 7x, since that's multiplication, those are not separate terms. The only thing that can separate terms is addition or subtraction. So 7x altogether is one term. So that is, say, term 1. Now let's use the text box. 7x by itself, term 1. Term 2 then would be negative 9y. Whoa. That's cool. Highlight thing. Term 2 then would be negative 9y. Term 3 would be just the negative 3 by itself. So terms are split up by addition or subtraction. And that's actually because of order of operations. Since addition or subtraction happen last, they actually kind of separate everything and say, whoa, don't do this till the very end. So that's why we let addition subtraction be the thing, the operation that separates terms. Now, if you do have a term, the numerical part of the term, usually the number in front of the variable, or you should really want to put it in front of the variable, is called the coefficient. So for the 7x term, the coefficient is just the 7. The entire term is 7x, 7 times x. That's the whole thing. The coefficient is just the 7. For the next term, the coefficient you could say is negative 9. And honestly, even though there's no variable with it, the negative 3 is also a coefficient. In real algebra, that's what we just say. We say, okay, even if it's just by itself, it's still a coefficient. It happens to also be the constant. Negative 3 is a constant. It does not attach itself to any variables up there. That's okay. It's still, in my book, it's still considered a coefficient. Now here's a key term. Here's a key concept. Like terms. They like each other. What that means is that they might have different coefficients, but they have the exact same variable setup. The exact same variable setup. So 7x and 3x, these are like terms. Different coefficients is fine, but it's because they both just have a single x attached to them. That makes them like terms. That means I can add 7x plus 3x. I would add their coefficients and then keep that variable portion the same. It's like saying I have 7 of this object, the object is x, and I'm adding 3 of that object together, so I'm going to end up with 10 of that object. This can only work if two terms have the exact same variable setup. And I mean not just the variables themselves, but the actual, any exponents on them have to be the same. So let's investigate that. I'm going to ask the question, are these like terms? I'm going to give you some examples. And you tell me if they're like terms or if they're not like terms. Like terms? Yeah, they like each other. I could add them together and actually condense them into something. So like terms, check. Nope, not that. Check. Yeah. And if I did want to, I don't know, maybe subtract one from the other, that would be negative 17y. I'm starting with negative 13 of them. I'm subtracting 4 off of them. So yeah, these are like terms. Good work. I'll put a smiley face. That's my attempt at a smiley face. I cannot draw. Don't expect me to draw, because I won't do it. I'll try. I'll attempt it, but it's bad. So yes, those are like terms. How's about 14y squared plus 6y? You're tempted to say they are, but they're not, because that's y squared. And when I say they have to have the same variable setup, I mean the same exact letters and the same exact exponents on those letters. So these are no. This would be a frowny face. It would be a frowny face. Let's keep on with this experiment because there's a lot of places it can get nastier than this. A lot of places it can get nastier than even this. How about orange? How about negative 7 x squared y z to the 4th plus 9 y x squared z to the 4th. Ah, it's tricky. It looks like they're not like terms because the x's and y's are in different order. That's okay. Remember, you can multiply in any order you want. So while they're not in the same order, remember, I can flip the order of multiplication. If I really wanted to, I could put this 9 at the end. Ooh, I could do that, and the expression is exactly the same. It doesn't matter. Now, my convention is to put the number, the coefficient, at the beginning. But I can switch now this x and y, or rather this x squared and y. It's the exact same expression either way. Suddenly, I have them in the same order as the previous terms, and each they have the exact same variables with all the exact same powers. X squared, y to the 1st, z to the 4th. X squared, y to the 1st, z to the 4th. These actually are like terms. These are like terms. And now it's like saying, I have negative 7 of something plus 9 of something. I just add their coefficients. What's negative 7 plus 9? 2. So I have 2, because remember that's the same as 9 minus 7. And then I have to just attach all that nastiness back there with it. So those actually are like terms. You just have to be a little crafty with them. One more thought. Heck, we'll throw a W in there. Like terms or no? Nope. They have the exact same variable letters. They have an X, a Y, a Z, a W. They almost have the exact same variable setup too, but not quite. This one's W squared, this one's W cubed. These are not like terms, and they cannot be combined. Now, maybe we could talk about factoring something out of that expression, but that's not quite the same thing, and that's something we'd have to deal with a little bit later. So they are not like terms, and so they get a big, fat, stinking frowny face. Okay. Right back to it. Okay, so like we mentioned last time, or just a second ago, rather, not last time, we have coefficients, we have a constant term, we have like terms, we defined, or we got some good examples of what like terms are, what it really means to be like terms. The last thing we'll look at, factors. That's just the parts that are being multiplied, the individual building blocks. 7x, the factors are 7 and x. 9y, the factors are 9y and y, or negative 9 and y. Really, the term factor just means it's a piece of something that's being multiplied to something else. That's all a factor is. And we are definitely going to be revisiting that term. Also revisiting a few of our properties of real numbers that we talked about. You can flip the order of addition. And so that's not only true for numbers like 7 plus 13 is equal to 13 plus 7. That's also true if you're attaching variables to things. That's also completely true. Because remember, a variable is just meant to represent a number. That's all a variable is at the end of the day. So real quick, out in the Zoomosphere, can you hear me? Is everything good? Just want to double check. Let me know, shoot me a message in the chat box. But I think you can. I see my mic lighting up. Very good. You're Gucci. Thank you. I am, I guess. Gucci. Okay, so we can switch around the order of addition. It's true even for variables. Same with multiplication. We have a commutative property of multiplication. So you could say x times 6. X times 6. That's a little bit sloppy. That's kind of a sloppy way of saying it. So what we like to put the 6 first. So we call that 6x. And that will, oh man, I have a bad joke. Y'all want to hear it? Stupid. That will be very 6x-ful for us. Successful. I'm surprised I got laughs out of that. I got some smiles. I think there's smiles. Of course, we're all wearing masks, but I think I got some smiles out of that. I see some raised cheekbones. The associative property, you can look at it. It just says you can regroup numbers. Look, the associative property is just not super interesting. I'll just call it like it is. Distributive property, though, is super interesting to us. We mentioned it last time. It not only applies for numbers, again, it applies for variables because, remember, a variable is just a symbolic representation of a number. It's a number we don't know. But if I can add, subtract, multiply, divide numbers, if I can distribute numbers, I can distribute variables all the same. And so that's what's going on here. If you had 5 times, in parentheses, 3x plus 7, you would just distribute the 5. It multiplies to the 3x, it multiplies to the 7. You keep that common sign that was in the middle, and you end up with 5 times 3x. Well, you just do the 5 times the 3, which is 15. The x doesn't change at all. So it becomes 15x plus 35. Same thing if you're subtracting. Inside, you distribute the 4. 4 times 2x. 4 times 2 becomes 8, but the x is just there because we don't know what it is. How can we multiply 8 by x if we don't know what x is? So we just leave it as 8x. So there's all kinds of things we can do to simplify an algebraic expression. And it's usually going to involve combining like terms. Combining like terms, that's something that is going to pop up a whole lot, a whole heck of a lot. So looking at this particular example, we'll work another one that's a little more complicated after this one. Looking at this example, here, if I'm trying to simplify that, there's no equation. There's no equal sign, so I'm not solving anything. All I'm trying to do is take the same algebraic expression, combine some like terms, do some distributing, and then we will simplify it as much as we can. So we'd start, this thing is just begging for us to distribute the 5. So that's 5 times 3x minus 5 times 7. And then there's just a 6x over here being subtracted. 5 times 3x is 15x minus 35 minus 6x. Even though they're not next to each other, are 15x and negative 6x like terms? Yeah, and according to the commutative property, even though they're not next to each other, if I really wanted to, I could reorder them so that they are next to each other. I could say that's 15x minus 6x minus 35. It's the same thing. All I did was move around the order in which I added or subtracted. And that's okay. In fact, they did that right here. They grouped them together over there. 15x minus 6x, get out of here, that's 9x. The minus 35, is that a like term with anything else? No. So it's just minus 35. It just sticks around there at the end. Let's work one that's a little bit tougher so we can have exposure to all kinds of things. Let's see, how about, what's a good one? What's an interesting one? How about, ooh. Everyone say, ooh. Ooh is right. That one's a little bit nasty, at least at the end. Ooh, thank you, Xavier. Very apt. Yes, indeed. Ooh is right. That one is not very pretty, but at the end, once we've solved it, we're going to go, ah. But wait for that. Well, we're wanting to simplify this. That is the goal. And it just looks like, from what we can see, it's just begging to be distributed. That there's things that are begging to be distributed. Namely, this 3 is begging to be distributed. This 9x is just 9x. It's just by itself. It's its own term because it's separated from everything else from it by addition. And you know what? Let's make this even a little bit harder. Let's turn that into subtraction. Ooh. Now what we're going to do is, now the 2x is begging to be distributed. And we're going to see how that goes. Mm-hmm. Exactly. Exactly. Yeah, you're exactly right. What we're going to do is, I'm going to show you some of the tricks we're going to be doing to get this simplified. But that's essentially what it's going to be. The special trick is where the 2x and the 15x multiply to each other. We're actually going to have to get an x squared out of that. We'll see why in a moment. But let's see. Let's try this out. Let's distribute the 3. And I'll write it out completely. I won't do any calculations yet. I'll just write it. It's 3 times 7 times the minus, rather, 3 times the 4x. The plus 9x squared, I mean, there's nothing special that happens to it. Now this next part, I need to be careful. We're doing minus 2x times positive 15x. So it's going to be minus 2x times positive 15x. I'll put them in parentheses just so we see how they kind of are related to each other. And then finally, we're doing minus, because there's a negative 2x over there. It's like saying negative 2x times positive 4. And then that plus goes away because there was minus 2x times positive 4. And a negative times a positive is negative. All right, well, let's see what we can do with that. What's 3 times 7? 21. Next up, we're doing minus 3 times 4x. Now the x is just x by itself. But I can do the 3 times 4, so I can get minus 12, and then I just slap that x back on. The plus 9x squared, I mean, it just isn't doing anything special just yet. It might combine in a moment with another like term, but it hasn't yet. Now, here's where it gets interesting. I've got minus 2x times 15x. Here's what I'm going to do. I'm saying 2 times x times 15 times yet another x. I'm going to rearrange it a little bit into a smart way. I'm going to put the numbers first, 2 times 15. Then I'm going to say times this x, this first x, times the second x there. All of that's being multiplied. I'll make that a little clearer that that's multiplication. And for this last one, I'm going to rewrite it. I'm going to put the 2 and the 4 together, because really I'm saying minus 2x times 4. But if you want to go even more than that, I'm saying minus 2 times x times 4. And thus I can rewrite the order of multiplication because of that commutative property of multiplication. So that's why the commutative property is important, because it allows us to kind of group things the way we want, to make it simple. And now let's use a nice maroonish, brown, whatever. The first 3 terms, nothing special is happening yet because we're not simplifying them. We already have. Now I've got minus, what's 2 times 15? 30. So it's going to be minus 30. And let me fix that because this is ugly. This 9 does not look like a 9. There we go. Minus 30. Then I'm doing x times x. What's another way to say x times x? X squared, exactly, because you're just multiplying something to itself, which is exactly what it means to be squared. Ooh, that means we just created a like term with the 9x squared. That's exactly right. And so we're going to simplify it even more in just a moment. And then finally, it's going to be minus 2 times 4 is 8, and then x is just x. But we can go even further down the rabbit hole with this. We can simplify it even more. I say be gone. Almost everything taken away. Let's bring this up here. Ooh. Now let's combine some like terms. So let's use a nice green again. 21, does 21 have a like term with anybody else? No, 21, its only other like terms would be other constants that don't have variables with them. So it's just 21, and it's just by itself. Now, even though they're out of order, does the minus 12x have a like term with someone else? Yeah, the minus 8x all the way down at the end. And so I can say negative 12 of something minus 8 of them. It's going to be negative what? 20. It'll be 20. Yeah, we'll do the x squareds in just a moment. But minus 12x here, the minus 8x becomes minus 20x. Finally, the last 2 like terms are this positive 9x squared minus 30x squared. They're like terms, obviously, because they have the exact same variable setup. They have different coefficients. Even if they had the same coefficients, they're still like terms. So if you take 9 of something and you take 30 away from it, you can't do that in real reality, but in theory, what would that become? Negative 21, exactly. Negative 21, oops, let me use green. Negative 21x squared. This was 21, this was also 21, just a coincidence. Nothing special about that. The very last thing we'll do is we'll rewrite in descending order. And all I mean is we've got basically the answer. We're not actually changing anything else except the order it's written in. Negative 21x squared, we want the highest powered term first, then we want to go down the line. So we're going to put, because we can use commutative property to rearrange addition and subtraction, that's going to be negative 21x squared. The next highest term would be minus 20x. And finally, that 21 is positive. This 21 up here is positive. So it becomes plus 21 at the end. And now this is the most proper way to express that. So this whole nasty business in red here at the top ultimately shrivels down to just this, and they're the exact same thing. You know, I just thought of something that bullies, you know, bullies, they're horrible. I hate bullies. Bullies at school are probably doing during this pandemic. They're probably, the kids they're picking on, they're probably pulling their masks and snapping it onto their face. Does that sound like something a bully would do? Yeah, I think it's something a bully. Let me tell you right now, don't bully. It's mean. I was bullied a little bit as a kid. Then I stood up to the bullies and, you know, life went on. So if you are getting bullied, tell someone, or yes, that's exactly right, Xavier. You know bullies are doing that to kids that they are picking on. Man, some people are just mean. There's mean people. I will never bully you. I'll prop you up. I'll say nice, positive things to you. If you say, Josh, I need a compliment today, I'll find a compliment for you. And it will not be mean. It'll be pleasant. It won't be a backhanded compliment either, where it sounds like a compliment, but it's actually a criticism. People do that to each other. It won't be that either. It'll be a true compliment. Okay. So that's another example. So we have finished the first section of chapter 6, and that's actually going to be what our test goes up to. It includes the first section of chapter 6, and then the first exam does not cover anything else in chapter 6, but we as a course do cover more of chapter 6. So we are going a little bit past what our exam is actually going to be covering. That's okay. It's not the end of the world. Let me bring up our next set of notes. And this is usually where I would tell some kind of witty joke, make some funny commentary. But unfortunately, as most of you have told me, I'm not funny. You say, I did a poll of my class and I said, do you guys find me funny? Just be straight up with me, be honest with me. I can take it if most of you think I'm not funny. Most of them did not think I was funny, and I could not take that. It ruined me emotionally. I was crying. I'm gonna see how long this joke can go on before it just gets uncomfortable. Of course, I'm completely kidding here. None of that ever happened, but I'm gonna see how long I can keep pushing this idea. Now I'm starting to get some laughs. All right. How many of you in the Zoom sphere or here in person, how many of you want to see a way that you can always be funny? How many of you want to see a method that will always ensure that you are funny, that you'll always get a group of people to laugh at you? Raise your hand if you'd like to see that. Does it include math? No, it's math free. Yay, and because sometimes we need a break from math, but I know secretly we all love it. We all love it 100%. And I'm still recording this, so if you're watching it in the YouTube video later, you will see. Thank you, Nicole, Xavier. Yes, I will show you a way that you can always be funny. All right, so I'm gonna have to use the whiteboard here. It's very serious, very methodical. Okay, we're gonna use a simple flow chart. Simple flow chart, not super mathy. It just says, all right, you're trying to be funny. You're gonna start, you're gonna tell a joke. Tell a joke, or you're going to have a funny story, or whatever it is that you're putting forth out there in the world that you're trying to be funny with. Tell a joke. There's two things that are going to happen. You tell a joke to your audience, and they're either going to what? They're either going to laugh and think it's funny, or generally speaking, they're not going to laugh. So you have two outcomes. You get those precious laughs that you were hoping for, or you don't. No laughs. Uh-oh, how many of us have found ourselves in that second situation here where no one's laughing at our joke? oh man, I thought this would be great. I, worked it out in my mind. I did it in my head. Okay, if you're there, here's what you do. I've been there, I promise you. Here's what you do. Make fun, oh, I can't spell today. Make fun of how bad your joke was. I'm serious. You tell a bad joke, and this is dead serious. It has worked for me. You tell a bad joke, it doesn't get any laughs. People look at you kind of funny, like, who is this person? So, okay, you say, wow, that one sucked. I didn't get that one off the ground today. That's okay. I'm not always funny. Every day, I wake up, I have these funny pills I take in the morning, and sometimes I forget to take those pills. I only take half a dose. That explains that last joke. You just keep going and going and going. You make fun of how bad your own joke was. People will laugh, I promise you. Here's the result. Here's the end result. Success, or 6x, as some people write it in mathematical terms. You either got the laughs or you make fun of how bad your joke was. Either way, you're going to get those laughs, and then it's going to fuel you afterwards. You don't have to eat for the rest of the day because you got all your energy from other people's laughs. It's kind of a weird alchemy thing, but it works. So I promise you that works. I will utilize that plenty of times. I don't tell math jokes because there's no such thing as a math joke, because math's not funny. So yeah, that's how you can always be funny. Come on, be close. Anywho, back to it, back to the grind. You're probably thinking, man, I wish that was like a 20-minute little tangent. No, you guys are funny. And if you're not funny, just make fun of how unfunny you are, and you will get laughs, I promise you that. It's time to hit the linear equations, and it's time to hit them hard. So we have to start off. We have some things we have to define. We have some forms we have to look at. A linear equation in one variable is an equation that can be written in the form ax plus b equals 0. A and b have to be real numbers. X is your actual variable. And then a shouldn't be 0 or else it's really not linear. So some quick examples of that. 3x plus 4 equals 0. That's a linear equation. It's only in one variable. It's only in one variable. What's another one? Well, how about x equals -7? That's also going to be a linear equation in one variable because the only two elements really rolling around are a single x, and notice that's raised to the first power. You don't have to tell, whenever something is raised to the first power, you don't have to write the first power. So that 1 up there is secretly in there. It's also secretly here. Notice it just says it can be written in this form. So even something like this, even something like that is an equation, a linear equation in one variable, because, as we'll learn here shortly, you can move things over to the other side so that everything is just on one side of the equation. You can rearrange the terms. So at the end of the day, it doesn't have to look exactly like this, where it's some number times x plus or minus some other number equals 0. They could be on other sides of the equation. They could be, you'd need to combine some like terms before it'll look like that. It just means it could be written as simple as this. That means you're not going to have x squareds going on. Whoa, x squared? No, it's just got to be a single x with perhaps a number in front of it and perhaps another constant number floating around out there. X squared is not going to fly. X to any power that's not 1. X to the 17th. None of that business going on. If your variable is x, you can't have a y in there as well. So this is not a linear equation in one variable down there because there's two variables. There's two variables, and so that completely just gets away from the definition. However, x is the most common variable you'll pick, but you can technically get crafty with it. If you just had y in there, that suddenly is a linear equation in one variable. We're just calling it the variable y instead of x. So this is okay. But if I threw a second variable in there and tried to pull them all together, no. So here's what we're trying to do, usually with linear equations. We are trying to solve them for the variable. We kind of did that earlier today. We had an example we looked at earlier where we solved an equation and tried to isolate the variable. That's great. We're going to see the mathematical tools we'll be using there. But yeah, solving an equation means isolating the variable and figuring out what numbers could I have substituted into the equation all the way at the beginning of it. What could I have substituted in for the variable and made a true statement out of it? That's all solving an equation is. We use certain methods to get to that. That's our end game. And finally, equivalent equations are two equations that have the exact same solutions. So x equals -3, the solution is -3. But even 4x plus 12 equals 0, the only solution to that is to plug a -3 in for x. You'd get 4 times -3, which is -12. Add 12 onto it, you get 0. So this first equation here, the only solution is x equals -3. The second equation here, well, obviously the only solution to that is also x equals -3. I wouldn't get too horribly caught up on the idea of an equivalent equation. Not super interesting. So one thing we can look at then is we can say, take a linear equation. Let's take 4x minus 100 equals 0. Four x minus 100 equals 0. What we're going to do with that is we're going to ask, hey, is this a solution? I'm going to give you a number, and you're going to tell me if it's a solution. So you might even be able to eyeball it. Which of the following, if any, are solutions to that equation? Let's try x equals 50. Yeah, you guys are shaking your head no, and you're right. Doesn't look like 50 is going to work. And the way I can tell is that I take that 50 and I plug it into x here. I do my math, follow my order of operations properly, and see if I'm going to produce a true statement out of that. So let's try it. 4 times 50 minus 100. And now I really shouldn't say it equals 0. What I'm doing is I'm asking, does it equal 0? So I'll just put a little question mark. Well, you can see that won't work. 4 times 5 is 20. So 4 times 50, you just multiply by 10 on top of what you just did, will give you 200. Is 200 minus 100 equal to 0? No. The left becomes 100. The right's still 0. 100, is 100 equal 0? No, of course not. This is a false statement. Thus, x equals 50 is not a solution to the original equation. It's just that simple. It's only a solution if you can plug it into the original equation and create a true statement. Now, you'll notice I use the term a solution, and I don't necessarily use the term the solution. It's because there are types of equations out there that can have more than one solution, more than one thing that's going to work. Quadratic equations, which we will investigate later, can have up to 2 separate solutions. So it just so happens in the case of one variable linear equations, there is exactly one solution. No more, no less. There will always be exactly one solution that works. We didn't find it here. 50 did not work, so we know it ain't going to be it. What do you guys suppose the solution really is? 25. Let's prove it. Yeah, I think 25 is going to do it. Let's check our math. How about x equals 25? We plug it in. For x, we substitute it. We're asking, is that a true statement? Well, 4 times 25 is 100. Looks like it's going to work. Yeah, 100 minus 100 is 0. Yeah, that works. 0 equals 0. True. True statement. True statement has been formed. Thus, x equals 25. The solution isn't 0. The solution is x equals 25 over here. What's interesting about this is we've found a solution to this equation, 4x minus 100 equals 0. It turns out, for reasons I just said, one variable linear equations have exactly one solution, no more, no less. So not only is x equals 25 a solution to the equation, it's the only solution because one variable linear equations have exactly one solution. How do I know that? Well, we won't prove that, but take it on faith for a moment. It can only have one solution. We found something that works, so we're done. So what we did was kind of a bad method. I just threw out some numbers to you. I said, okay, try 50. You could have tried 75. You could have tried 10. You could have tried 0.3. You could have tried negative 2/3. I just threw out numbers. Now, it just so happens you can kind of tell the answer to that was supposed to be 25. But there might be others where the answer is not so obvious. So do you think this guessing and checking method is a good method in general? No. We happened to get it on the second try, but it's because I engineered it to be like that. Yeah, guessing and checking is bad. Guessing and checking is a terrible way to solve equations in general. No, don't do it. You don't want to do it. Here's what we're really going to do. We're going to solve our equations just using some simple mathematical principles. And I'll state this one. We're also going to invoke the idea of the additive inverse and the multiplicative inverse. We're going to invoke those ideas and we're going to see how we can utilize them in order to solve these equations. So the addition property of equality says if you have an equation, you've got two things on either side of equation. It could be as simple as A equals B, or it could be A represents a nasty mathematical expression. B represents a nasty mathematical expression as well. But if I choose to add a number to both sides of that, as long as I do it equally to both sides, as long as I add the same value C equally to both sides of the equation, I'm set. It's going to change maybe the way the equation looks, but it's not going to change the solutions, which is what I'm finding. It's not going to change the solutions to that equation. In other words, I can be tricky and I can manipulate equations the way I want, perhaps by adding something to both sides of it. Since addition and subtraction are the same, this means I can also subtract anything I want as long as I do it to both sides fairly, and it's the same thing on both sides. Let's look at the details on that. Let's say your goal is to isolate your variable x. And let's say that x plus 16 equals, I don't know, 30. Let's say this is your equation you're dealing with. This is your equation you're dealing with. Here's a few things you can do. You can add any number you want to both sides. You can subtract any number you want to both sides as long as you do it both. So why don't we, just for fun, why don't we add 5 to both sides? Why am I doing that? Because I can. Anarchy, right? I can do whatever I want. So I'm going to add 5 to both sides. Okay, well, let's see. That's going to be the x is not a like term with the 5. I'm going to do the 16 plus 5. I'm going to get 21 over here. On the right, 30 plus 5, I'm going to get 30 plus, or 35, excuse me. So after adding 5 to both sides of the equation, I'm left with the equation x plus 21 equals 35. Am I any closer to solving that than I was before? Not really. X plus 21 equals 35 is about as complicated as x plus 16 equals 30. We want the x to be isolated. We want it to be by itself. So adding 5 to both sides didn't do me any good. I can do it, but why? Why should I? And the answer is I shouldn't have. It doesn't help me, but it is something I'm allowed to do. What should I do instead? Subtract what? Perfect, you're absolutely right. Instead, I should be subtracting 16 from both sides. Because if I do that, I can add or subtract anything I want. If I do that, when I combine the like terms here, the 16 is going to be gone, isn't it? We're just going to be left with x. The right-hand side, I got to do 30 minus 16. What's that going to give me? 14. And now I've actually solved it. It's in the bag. I've got 14 as my answer because x is all by itself. So while I could have added 5 to both sides, I chose to subtract 16 instead, and that worked. It also makes sense. That's where that additive identity of addition comes from. Since we were adding 16, what I wanted to do to get rid of it was to take the opposite sign and add it to both sides. Add negative 16, which is the same as just subtracting 16 from both sides. That took care of business for me. So the addition property of equality, I can add anything I want. So be smart. Pick a smart number that's going to help you reduce and simplify the equation. The multiplication property of equality says that if I have some equation, one thing equals another, I can multiply both sides of the equation by any number I want, as long as I do it fairly to both sides. Okay, so once again, this means, okay, I could multiply both sides of an equation by 2 if I wanted, but if that doesn't help me, why do it? So for example, if you had 3x equals 24, I could multiply both sides of that by 2. As long as I do it to both sides, I haven't broken any rules. But then that would just give me 6x equals 48. Did that help me any more in getting this thing solved? Not at all. So instead of multiplying both sides by 2, what should I do instead? Exactly, I should divide both sides by 3. I'm allowed to divide because multiplication and division are secretly the same thing. And if you don't like the term divide, we'll just say you're multiplying both sides by the reciprocal of 3. So you can either say I'm multiplying both sides by 1/3, or I could say I'm dividing both sides by 3. Either way, this is going to cancel. 24 times 1/3 is the same as 24 divided by 3. If you don't believe me there, go back to your definition of multiplying fractions. What's 24 divided by 3? What times 3 gives you 24, and it's 8? Yep. I could multiply both sides by any stupid number I want, but doesn't help me. I need to be smarter about it. One number I definitely won't want to multiply both sides of an equation by is 0. But you can, if you multiply both sides by 0, you just get 0 equals 0. You've completely knocked your variable out of the universe if you do that. So you can multiply both sides by 0. It still produces a true statement, 0 equals 0. It's just not an interesting one because your variable's gone. So you're just not usually going to multiply both sides of an equation by 0. What if you started with this equation? 2/3 x equals 16. Or even 2x over 3 equals 16, which is actually the exact same thing. It's the exact same thing. Exactly, you're on the right track, yeah. What you're gonna do is you can get rid of the 2/3 over there, which is what you wanna get rid of. You could start by multiplying both sides by 3. As long as you do it to both sides, you're golden. Those 3's will cancel, leaving you just with 2x. 16 times 3 is 48. Exactly. And then now you would divide both sides by 2 slash multiply both sides by 1/2. I'll call it division this time. 48 divided by 2 is 24. That's one way to do it. It works. Notice though it kind of took 2 steps. Maybe there's a slightly more efficient route we can take. And there is. Let's go back in time. Back in time. There we go. We could multiply by the 3, then divide by the 2. Or we could do it in one fell swoop by taking the reciprocal of this number. 2/3 times x, multiply both sides by the reciprocal according to that rule. Let me write it a little bit better because I wrote a giant 16 over there. So let's put that on. Multiply both sides by the reciprocal of the number that's in front of x, the coefficient of x. What that's going to do for you, those are going to go away. Because when you multiply a fraction or any number by its own reciprocal, they just multiply to 1, and you're just left with 1x. But if there's a 1 in front of something, that's the same as just, you don't need it. The 1 is called an understood one. And then over here, call that 16 over 1, if that helps you do the multiplication. Now we got to multiply 2 fractions. You can use cross multiplying. You get 8 times 3 on top, which is 24. You get 1 times 1 on bottom. Of course, something over 1 is just itself. Little water break for me. So yeah, those are some of the basics behind equation solving. All we're doing is manipulating the idea that I can add or subtract anything I want from both sides of an equation. It can be a number. It can even be the variable itself. I can also multiply slash divide both sides of an equation by anything I want, but you don't want to do 0. You shouldn't multiply by 0. You certainly can't divide by 0. And so that's all those properties are telling us. So we can look at this little table here. Exactly, it is, yeah. It is the same exact thing we just went through. It's just saying x minus 3 equals 8. I could add 5 trillion to both sides if I wanted. Why do that? Add 3 instead, and you'll isolate the x. The solution then is 11. They put these little squiggly brackets around it, saying this is the set of all solutions. We'll talk about what set theory is in the 1332 portion of the course. Over here, subtract the 7 over to get x by itself. 6x and whatnot. What if you've got both of them going on? What if you don't just have one thing you got to do, but you got to do 2 things or 3 things or 4 things? Well, that's going to be okay. It's not going to kill us. Our goal is ultimately to isolate the x. It's ultimately what our goal is. So you would do any like terms you can combine. You want to isolate the x with its coefficient as soon as you can. In other words, add or subtract whatever you have to from both sides to get the x by itself with its coefficient. Then you're going to get rid of the coefficient by multiplying both sides by the reciprocal of the coefficient. Let's try a couple of these out. We're going to see a lot of cases here. Let's solve that one we did earlier that we were looking at. And actually, I think it was minus. So, and let's make that a better 0. (4x minus 100 equals 0). Our goal is to isolate the x. The first thing we're going to want to do here is do what? Move the 100 over. Does everyone see that? Because that will get the x by itself. It'll still have the 4 in front of it, but that's at least one step in the right direction. So I'm going to add 100 because that's the opposite operation of subtraction. So now we have 4x equals 100. Now we can either divide both sides by 4, or you can say multiply both sides by 1 over 4, whatever you're comfortable with. And maybe you can see it, maybe you can't, but 100 divided by 4 is going to be 25. Unsure? Do some long division. 4 won't go into 1, it'll go into 10 twice. Bring down the 0, 4 goes into 25 times. In fact, it does so very cleanly with 0 remaining. So yeah, x equals 25 works. How can I tell if that's the right answer? Exactly, plug it in. Exactly right. Yeah, just take the 25 and go plug it all the way in before you did any manipulation of the equation. Plug it all the way in back at the beginning and make sure you come to a true statement. So we know how to check solutions, but just randomly guessing at what a solution could be is not a good system. We need to use these solving methods. Let's get some more interesting ones under our belt. So our goal for all of these is just going to be solve. Perfect, absolutely right. Start by combining like terms. So usually combining like terms is going to it just makes sense to do that. Because if I combine like terms, I can condense everything down into just one appearance of the x. So it's not showing up in multiple places. Yeah, I'm going to combine like terms. 17 is untouched. 6x minus 19x, well, what's that going to be? Negative 13x, yep. Then I can divide both sides by what? 13, and is it 13 or negative 13? Very good. Yeah, we'll divide both sides by the coefficient of x here. And it's okay that the x is on the right-hand side. Doesn't affect anything. We say that equations are reflective or reflexive, or no, I'm sorry, symmetric, excuse me, which means I can flip them. So, long story short, this just becomes 17 over negative 13 is the same as just negative 17 over 13 equals x. Or if you like your x's all on the left-hand side, because we like to read from left to right, you can write it that way. Let's do yet even a couple more nasty ones. Let's do a couple nasty ones. And they can get nasty, they can get awful nasty, awful quickly, I promise you that much. How about okay, so it looks bad. Let's just break it down as much as we can. If you see something that could be distributed, should you do it? More often than not, yes. Those things that look like they could be distributed, kind of looks like they're asking to be distributed, and that's exactly right. We're going to do our distributing. And on the right, we'll combine like terms in a second. What is this part going to distribute as? Perfect. Very good. Exactly right.
Addition and subtraction.
Exactly. So combine like terms. Yep. Yeah. We'll combine like terms. We'll combine these over here. What's negative 12 plus 7 going to become? Negative 5. Yep. The 3x didn't have any like terms on the left-hand side, so we leave it alone. 9 plus 2 plus 24 will be what? 35. 11 plus 24, 35. Now we have a couple options. We can add a number, any number we want to both sides of the equation, right? Or I can subtract a number I want. So let's just get rid of that 5 on the left-hand side. It doesn't matter if you do the 5 first or not. It's clearly a like term with the 35, not the 6x, so we'll write it under there. Yeah. The 5 is gone on the left-hand side. 35 plus 5 is 40. You still have minus 6x over there. Exactly. That is exactly right. We can add any number we want to both sides, but since variables just represent numbers, I can actually add any variable expression I want to both sides as well. So exactly, I'm going to add this 6x over. Now I'm running out of space, so let me adjust a few things. So now, on the left-hand side, what am I going to be left with? 3x plus 6x is going to give me 9x equals, what's the only thing left on the right? 40. And now all I got to do is divide both sides by 9. $40 over 9, does that simplify? It won't. 40 is, the 9 is 3 times 3. No 3's can be divided out of 40. So, I mean, 40 over 9 is just the answer. Let's look at one more, because this is crucial. You have to be able to solve these one variable linear equations. It's got to be down pat. So 40 over 9 is the answer to that one. Next up, let's solve. Let me make it interesting. It looks bad. I'm sorry, I meant to put squareds on these. Ooh, dun dun. Squareds, but Josh, you said that squareds, x squared makes it no longer a linear equation. That was like one of the examples you used at the beginning. Yes, you're right. Yeah, let's see what happens though when we actually do anything with them. Let's see what happens. I'm sorry, did I? Let me double check my math on this. I might have wrote something down wrong. I'm not quite sure what I was thinking, but let's make this, hold on, let me do some quick mental math. Okay, I'm sorry, let's not make this first one and a squared. That's okay, that's what I did. I just put squareds on the wrong thing. This is gonna be our equation. So that 5x does not have a squared on it anymore. What's the very first thing I should do with this? Yeah, I'm going to distribute. Oops. That was a 4. There's no distributing on the right-hand side. 3x times 4 becomes 12x. Now we had minus 3 times 2 is 6. X times x will be what? X squared. On the left, the only thing we can, or excuse me, on the right side, the only thing we can do is combine like terms. Those aren't like terms. 9x squared minus 15x, what's that going to become? 9x squared minus 15x squared. 9 minus 15, that'll go negative. 6x squared, very good. Once you know it's negative, then you really do the 15 minus 9. Now you're still saying, Josh, this is not linear. There's x squareds going around. Not for long, my friend. That's why I had to engineer this very carefully. If I try to, say, move the 6x squareds over, they go away completely, don't they? Yeah. So this one had a little tomfoolery in it. It was tricking me. It's not actually a quadratic like it looks like an x squared problem. The 6x squareds are gone. Oh, that's not so bad. We can move the 5x over, but after this, it's just clean up. It's linear. You can move the 7 over, or the 7 over. 7x will be equal to negative 3. You can divide both sides by 7. You're going to get negative 3/7. Okay, let's call it for today. If you're here in Zoom, I already got in touch with you and got you down for attendance. Very good. Real quick, let's remember the order of events for next week. Tuesday, we are going to meet, but not physically. We are only going to meet Tuesday in this Zoom setting, in the online Zoom setting. So we'll still meet during our usual times on Tuesday in Zoom. Thursday, we will also not meet person to person. We won't meet at all, neither person to person nor virtually, because Thursday you're going to have your exam. So Thursday, September 10th, you have your exam. You have the instructions in that Canvas announcement, so you can get more information. We use the Respondus Monitor system. Tuesday, when we meet, we might lecture over some new information, but I also want to use Tuesday as kind of a review day, an opportunity to review some of our stuff. And then we won't meet again face-to-face until Tuesday, September the 15th, so almost 2 weeks from now. So keep that in mind. Thank you for showing up in the Zoom room. You guys have a lovely day.